Hello everyone, and welcome to the next webinar of our BRE 600 series. My name is Václav Miklas and I work at the European Bryan Research and Engineering Office in Brno, Czech Republic as an engineer responsible for ProMax licensing, training and support in Southern and Central Europe. And today, the topic we'll be discussing is debottlenecking of an amine sweetening unit. Amine systems, they are not really money makers, but very often they can become money wasters if they are not working properly. They can limit the overall production of the facility, and it's definitely not something we want to see. It's very common to see a need of operators to either increase the capacity or fix some issues, and so it's no surprise that it's actually one of the most common units we help our customers with. And that's why I decided to do this webinar for you. And I'm glad that so many of you have joined me today. So we'll basically look at a very practice-oriented problem, looking at an amine system and how you can use a process simulator ProMax to basically identify and overcome bottlenecks. So let's take a look at today's agenda. We'll start with a bit of theory. I will explain to you how in ProMax you can evaluate driving force in absorber and how can use this knowledge to better understand the process. And also, based on this understanding, we can come up with some corrective measures to fix this mass transfer pinch where we are approaching equilibrium in our absorber. After that, we'll move on to simulation. So we are going to open a ProMax simulation, and I don't know how about you, but I'm a very curious creature, and very often, I ask myself a question like, I wonder what does this red button do? And doing these what-if scenarios is something that is really easy to do with ProMax. We're going to discuss the base case, and after that, we're going to ask some what-if questions, and we're actually going to investigate how this amine sweetening unit would perform with a different amine. And we're not only going to look at it from, say, basic perspective, we're going to get in a lot of detail, and we're going to use quite complex ProMax model, including some equipment rating, to basically predict how different pieces of equipment would perform with different amine or at different conditions. So this is today's agenda, and let's start with the theory I promised to you. First part is driving force in absorber. In ProMax, we have two quantities that you can evaluate. We call them lean and rich approach. And these are basically approaches to equilibrium in your absorber. And the way it works is that if you have 100% approach to equilibrium, you are at equilibrium. There is no driving force available for the mass transfer, which means that there is no absorption. It's a similar idea as if you have a heat exchanger and there's no temperature difference either in a given point. That means that there's no heat transfer and you get a pinch. And you can also get a mass transfer pinch, which is something we can investigate using ProMax. And this is really helpful because it can tell you if there's a bottleneck, either if your unit is not performing well and you want to see what's the limitation, or if you are thinking about increasing the capacity, about pushing the unit to a higher limit. Even if the unit is working properly and you're not thinking about decreasing the capacity, these approaches can also tell you something about the stability of the process, especially when there are some process upsets. For instance, there's some problem with circulation pump in your amine unit and you don't have as much amine available in your absorber. Or there are some fluctuations in your feed, either in terms of concentration or in terms of flow rate. What can also happen is that there's some problem with regeneration part, for instance, or it might be a very hot day and your air coolers are not able to take it. So there can be a lot of problems or upsets in your amine sweetening process. And it's good to make sure that the unit can take it, that it is robust enough to, even if these bad times, it is able to meet the specification and work well. One more note I have here is that the approaches are calculated on a per component basis. Since in amine sweetening, we very often have simultaneous removal of H2S and CO2, it is advantageous to see the bottlenecks separately for these two components. So that's just a side note. And also what might be worth mentioning is that this concept of approaches, it is applicable to basically all solvent-based processes. So we are going to demonstrate it on amine sweetening today, but it would work on many other processes as well. All right. So this was the concept in general. Now let's take a look at lean approach first. Lean approach refers to the amount of driving force we have available at the top of the absorber. So as you can see, it is the driving force between the lean solvent, lean amine in amine sweetening, and between sweet gas, the vapor leaving at the top of the column. And the way we calculate it is based on fugicities. So as you can see, we basically take fugacity of a given component in liquid phase in the lean amine stream and divide it by the fugacity of this component in the sweet gas in the vapor phase. And based on that, we are able to calculate lean approach. If these two fugacities are the same, then we are at equilibrium and lean approach is going to be 1 or 100%. What it says is what is or how far we are from the maximum attainable purity with our sweet gas for a given lean amine stream. So, with the residuals of H2S and CO2 that are in the lean amine stream, how pure sweet gas we can get. And the word purity is very important, so I want you to remember it because it will be useful when we are discussing the corrective measures in a bit. Let's take a look at rich approach. This is where we're looking at the bottom of the absorber and the driving force between the sour feed and the rich solvent. As you can see, we are still using fugacities for the calculation, but in this case, we're using it indirectly. So we are basically figuring out this minimum or equilibrium flow rate of amine for which the fugacities are equal to each other, just like before. And we divide this minimum flow rate with the actual flow rate if in our absorber. And this kind of gives you an idea that in this case, what's important is quantity of amine. So since it is based on flow rates, it is basically about how much amine we have available in the absorber. And even if you are not looking at a simulation and you are not calculating approaches by ProMax, you are still able to see some indicators for existing units when it comes to whether a rich approach is too high or too low, for instance. As you can see, if the operation is likely at rich end pinched, when we have high rich approach, you very often see temperature bulge, this maximum temperature, somewhere in the top third of the absorber. And this basically tells you at what location the reactions happen at the highest rate. And if they're happening in this location, it tells you a couple of things. First of all, you are dangerously close to the top of the absorber, so you're close to acid gas breakthrough. And also here, not too much is happening, which probably means that by the bottom of the absorber, you're running out of amine. It also can tell you something about the opposite case. So if you see a temperature profile similar to this, if you have a few thermocouples along the absorber or you have an infrared thermometer, you might see something like this, and it might tell you that your rich approach is too low, that you might be over circulating. Okay, so this was the concept of approaches. Now let's think about what would be good corrective measures if we have either rich approach or lean approach too high. So let's start with a lean end pinch. So let's say we have 100% lean approach, and that means that the lean amine is in equilibrium with sweet gas. What do you think would be a good fix for this case? June is suggesting reboiler duty, and that's correct. As I said, the key word here is purity, and if we don't have pure enough amine, that means that we need to push our reboiler a little harder, regenerate a little better to make sure that we push the lean approach to lower values. Let's take a look at the other one. So the rich approach, and what would you do if the rich approach was 100%? How would you fix it? Yeah, that's true. We need to increase amine circulation. Since we are running out of amine, we don't have enough moles of amine available to react with H2S and CO2. We simply need to put more amine there by increasing circulation or by increasing strength of our amine. Here we can see it all summarized. So we have two approaches. The lean approach corresponds or reports driving force in the top section of the absorber. The keyword is purity, and if it's too high, we can fix it by increasing regeneration, increasing the reboiler duty. For the rich approach, we're talking about the bottom section of the absorber, and it is important in terms of quantity of amine, which is why we need to increase solvent strength or circulation if we want to push it to lower values. All right, so this was the theory. Now it's going to be all practical. So what I'm going to do now is to open ProMax. We are going to basically take a look at this amine unit. And it is not a real facility, but I basically picked a lot of bits and pieces working with our clients. So, and the problems that they encounter. And I put it into this one conglomerate, this one simulation, which we will be working on together. As you can see, we have a DEA unit. And if I open this sour gas and go to composition, you will see that we have something like 0.5% of H2S and 3% of CO2. And our goal, since there's some cryogenic processing downstream of this amine unit, is not only to have ppm levels of H2S, which is quite common, but also to have below 50 ppm of CO2. So we basically have simultaneous removal of H2S and CO2 down to ppm levels. The layout is quite typical. We have an absorber, we have a regenerator, we have a circulation loop between. And what we also have here, as you can see marked with these numbers, are some operating issues. The operating company, they have problems with fluctuations of their sour feed. Right now, we have 111,000 cubic meters per hour, but it can get to 115 at times. So we have some fluctuations. The problem is that if we are at 115, they have experienced that their sweet gas was off spec. The other problem is that they have a similar off-spec problems on hot days. So if it gets too hot, and if I open this inlet air stream, you will see that we already have, say, bad case scenario here with 30 degrees Celsius. But if it's worst case scenario and it's 35, they have experienced that they weren't able to meet the specification. Another problem related to this is that they have limited footprint, so they're not able to easily expand their air cooler section. So this is something they need to deal with. The third problem we have here is that they have, say, sporadic corrosion issues. It's not very bad, but they have seen more frequent plugging of the lean rich heat exchanger and their filters on the rich side. And they suspect that the reason might be that their rich loading is quite high for DEA. Right now is not a disaster, but if they could, they would like to fix this. And last but not least, they are also operating the reboiler at the maximum capacity, so they are not able to push more than 12 tons per hour of steam through it. In most of the cases, they are able to meet the specification, but they know that the process is not very stable and it's not very sustainable in a long term. So they would like to investigate this a little more to see what is the actual problem and how they might be able to fix it. The first step I would recommend to do is to calculate approaches to see how the driving force stands in the absorber. The way you can evaluate this is that you open the absorber, and it is actually created as a specification. So we need to go to specifications, and I can click on add to add a new specification. And the name of this one is quite straightforward. If I want to create lean approach, I need to select lean approach. And we're going to start with H2S. As I said, it's separately for the two components. So let's first create lean approach of H2S. Once I click OK, I will see this dialog. I will need to pick the stage. Since lean approach refers to the top section, we need to pick stage number 1, which is at the top. Sometimes you might have top-down numbers of your stages. So, the top stage can actually be 20. And don't get confused. In this drop-down, actually, what's at the top here is also at the top in the column. So I am sure that stage number 1 is my top stage. Exiting phase, there's the sweet gas, so that's vapor. And we just need to pick H2S. Now I'm going to do the same thing for CO2. So lean approach of CO2. Stage number 1, exiting phase is vapor, and component is CO2. And now we can move on to rich approach. So type of specification is rich approach. Let's start with rich approach of H2S. Rich stage is the one at the bottom. Lean feed. Here we clearly know that it is definitely not sour feed. But again, ProMax is helping you out. The stream that is attached to the top of the column is also going to appear at the top of this dropdown. So I know it's stream 22, and I can select H2S and click OK. Let's do CO2 real quick. Okay, so here are the results. The next thing I'm going to do real quick is, in order to report these values on your flow sheet in a property table, we need to first add it to what we call a short moniker list. I would like to do this because it's going to be easier for us afterwards to see the values without clicking into the column. And just to get back to the short moniker list, it's basically a list of shortcuts, just like on your desktop, or it's a list of favorites, just like in your web browser. And if I click on this lean approach of H2S and click on add to short moniker list, I can basically afterwards click on this add/reset short moniker to add it into my list of favorites. I'm going to do this with all 4 real quick. And after I'm done, I can go to ProMax streams, add a property table on my flow sheet. And here you can see a couple of radio buttons. If I select moniker, you can see short moniker is selected in default. And here I can see my list of favorites, and I can add lean approach of CO2, H2S, and rich approach of CO2 and H2S. All right, so we have the results here. And what kind of conclusions can we make? Lean approach of H2S is attacking 100%, which means that even though we are within the specification, if there are some problems with regeneration, it can send us off spec. So that's one thing. It also tells us that the reboiler is probably going to control the H2S specification. So this is actually useful for us to know that reboiler can be used as a control mechanism. If we take a look at rich approaches for both H2S and CO2, they are around 80. It might not look too bad, but in most of the cases, when you are getting 280, over 80, it's kind of a dangerous zone. It's better to keep it below that. Say 70 is typically a reasonable trade-off between stability of the process and between over design. So we don't quite like these reach approaches either. And now we kind of have an idea that it might be good to increase the regeneration, which we can't really do because the reboiler is maxed out. We would like to increase the circulation, which we might be able to do because the pump is not a bottleneck. But we also know that the air cooler is not really doing a proper job, even at this flow rate. So it will probably get worse. And with this basic idea we have, it would be good to see what actually happens, to try different scenarios, to tweak the simulation a bit. And in that case, what you want to have is kind of holistic model. You want to include the details of the model. You want to make sure that you also think about the equipment constraints, for instance, which is why this simulation is including some of these aspects. As you can see, for instance, for the air cooler, we have the air side here. So this heat exchanger is actually rated, and we are able to predict this outlet temperature based on the heat transfer predicted by ProMax. And there's more to this. So let me take you through all these small things we have here in terms of equipment information. And after that, we will investigate a couple of scenarios. We'll see how the unit performs when the fluctuations occur, when it's a hot day, what would happen if we increase the circulation rate. So we're gonna do all that after I'll give you this excursion. Let's start with the absorber. So if I open the absorber, go to process data in general, you will see we have geometry here, which you have to have for all the Amine absorbers. And based on the geometry, we can, for instance, keep track of fraction flooding. As you can see, it's somewhere between 70 and 80, so that looks quite reasonable. It's not really bad. But once we start playing with the simulation, we might want to take a look, keep an eye on this. So that was the absorber. For the flash tank, as you can see, we have a couple of numbers here. The red ones are the actual size of the flash tank. So it is 10 meters long, 3 meters in diameter. But we also have some other numbers here, and these come from ProMax separator sizing. If I open the flash tank and go to sizing, you will see that basically I put here some numbers that were very likely used for the design and that give us similar results to what is actually in operation. Based on this, we basically can have some sort of predictive calculation if we change something in terms of circulation, and we want to predict if we're still able to, have the appropriate size for the given hold-up time and for the separation we would like to desire. That's what this separator sizing is doing for us. If we move on to lean rich heat exchanger, and I double click into it and go to rating tab, you will see that we have geometry of this shell and tube heat exchanger here. So, it is something like 0.6 meters in diameter. We have 6 meters long tubes plus heads. So we have this one pass shell and tube heat exchanger, just one shell. It's fairly simple. And based on the geometry we have here, ProMax is able to calculate area available. So this comes from the geometry. And it is also able to calculate area required. This comes from heat transfer equation. So you basically have Q dot equals U times A times delta T, which is that the heat UT equals the overall heat transfer coefficient times area times the mean temperature difference. And from this equation, you're able to express the area required. We know the heat UT from the balance, and ProMax is able to calculate overall heat transfer coefficient for us from the physical properties and the flow regimes and velocity, etc. And ProMax is also able to figure out the corrected effective mean temperature difference. And based on that, we are able to find out this area required, which is bound to the real heat transfer happening in the heat exchanger. And as you can see, the two areas are actually very similar to each other. This is not a coincidence. In order to predict the real performance in a heat exchanger, you want to have fraction over design of 0. So you basically want to have heat transfer and heat balance in line. And the reason why it's so close to 0 here is that I have a solver created in this outlet stream from the heat exchanger on the temperature. So it basically tweaks iteratively, this solver, it tweaks the temperature to change the heat transfer or change the heat UT. And since heat UT is part of the heat transfer equation, it changes the area required and changes the fraction over design. And based on this, with a few steps that are all handled by ProMax, we are able to tune the fraction over design to be 0, and we are basically able to predict the real temperature coming out of the heat exchanger. So this is based on the real geometry, based on real heat transfer. Moving on to the stripper, just like for the absorber, we have geometry put in. And as you can see, in this case, fraction flooding is already getting quite high, especially at the bottom. We have 85%. So not only that the reboiler is operated at its maximum, we also have quite flooded column, which could be a problem if we want to increase circulation rate. For the pump, as I mentioned before, it is not a constraint here. If we wanted to make it a bit predictive, in ProMax you are able to put performance curves for a pump, for instance. But as I said, here is not a concern, so we don't have any information about the pump put in here. However, for the air cooler, we do have heat exchanger rating again. So if I open it and go to rating, the same idea about the areas and forcing fraction over design to 0 with the solver. The solver is created on this lean Amine temperature. So this again pushes fraction over design to 0. We have one more solver here on the air flow rate. If I go to this air outlet stream and I can see another blue cell here, which means that there's a solver behind it. If I open the solver, you will see that this one is forcing the total fan power to 12 kilowatts. So it is basically a constraint of our electric motors that are driving the fans in our air cooler. All right, so this was all the equipment constraints or information we put into this simulation. And now we can finally get to some fun studies that we can run on a ProMax simulation. So what I'm going to do is that I will save this file, and I'm going to show you a really wonderful feature we have in ProMax. So you might be aware of it, but if you're not, it can be very useful. What you can do with ProMax is opening an unlimited number of instances, running the simulations side by side, comparing them together. So what I'm going to do, I'm going to copy this DA base case, and I'm going to paste it here a couple of times. And this is going to correspond to a couple of case studies I'm going to run. So for this first one, it's going to be the case of fluctuation when the flow rate is a little higher. The second one is going to be hot day. So when the air is say at 35 degrees Celsius. And the third one is going to be more Amine. And what I can do now, which is one ProMax license, I can open all three of these files and I can let them run and I can compare them afterwards. All right, so the files are loading slowly but surely. So we have case A, case B, and case C has just loaded as well. And what I'm gonna do now is that I will open the first case A, and I'm going to increase the sour feed flow rate to 115. And I'm going to execute a flow sheet. And while it's solving, I will move on to case B. In this case, we are going to increase the air temperature to 35 degrees Celsius. So I'm going to open this air inlet stream. And instead of 30, I'm going to increase it to 35. That's basically as hot as it gets in the Czech Republic. So let's consider it the maximum temperature. And let's execute it. And the third one is the one with higher circulation rate, where I'm gonna open the outlet stream from the makeup block, which is where the flow rate is controlled. And instead of 110 cubic meters per hour, we're going to circulate 120. So now if I open my task manager, you will see that my processor is working quite hard on all three simulations. And if I go back to the simulation A, it might be getting to a solution soon. We have a question. What was the original reboiler duty? To be honest with you, I'm not sure. I know that it was 12 tons per hour in terms of steam flow rate, but we can easily check if I go to the base case while these are solving and open this Q reboiler. We have a little over 7 megawatts of reboiler duty here. And we haven't changed it. This is fixed, operated at the maximum that the reboiler can do. All right, so it looks like we're getting some results. Let's take a look at the results now. So this is the case where we have higher sour feed flow rate. And as you can see, the process really is not very stable, since if we are at 115,000 cubic meters per hour, we can see the CO2 concentration to completely skyrocket and be at 400 ppm, which is way over specification. So this is why it was such a huge concern for them and why they've seen their sweet gas getting off spec. And the ProMax simulation just confirms it. If we take a look at the approaches and we compare it to the base case, so I can easily put it side by side like this, we will see that the rich approaches has gotten worse, which definitely makes sense. And as you can see, even though we are not even close to 100%, we're just pushing it a little closer to 80 and over 80. We are already off spec, and the process is really sensitive around this area. We're kind of operating at the edge, and it's really easy to be pushed over the edge. What is also interesting to see is that the lean approach has actually decreased a bit. The reason is that the position of pinch has moved even more towards the bottom. So this is really our bottleneck, and it actually limits also the sweet gas purity more than the lean amine purity, which is why we're seeing the lean approach of H2S decreased slightly. All right, so this was case A. Now we can take a look at case B, which is the hot day. And again, I can put the simulation side by side and take a look at what's happening. In this case, it's not as bad as in the case of higher flow rate, sour feed flow rate, but we're still off spec with CO2. And if we take a look at approaches, they are almost the same. They haven't changed too much. So what is actually the reason why the performance is worse? The approaches, they are describing mass transfer. So these are about fugacities or partial pressures, if you will, between the vapor and liquid phase. But in the liquid phase, what's also happening are the chemical reactions associated with amine sweetening. And these reactions are exothermic. That means, in terms of equilibrium, that they are favored at lower temperatures. And if we get to higher temperatures, so, lean amine is instead of 51 at 55 degrees Celsius, the equilibrium is so hurt that we are off spec with CO2. Now let's take a look at the last case, which is the higher circulation rate. With higher circulation rate, the rich approach has gotten a little better, but it looks like the lean approach of H2S is really close to 100%. Let's see what it does with the specification. As you can see, we are at 13 ppm, so we are off spec. And it really just tells you how regeneration is important for H2S specification in this specific case. So once we increased the circulation rate with the fixed reboiler duty, which is the maximum we can get through the reboiler, we are not able to regenerate as good as before, which means that the H2S absorption, which is limited by the purity, is getting significantly worse. And this is also confirmed by the lean loading. So lean loading, this is basically just like for the rich loading. This is a relative measure of how much H2S and CO2 we have bounded to our amine. And you can see the amount of residuals of H2S and CO2 in our lean amine for the higher circulation rate is, because of the struggling regeneration, significantly higher, say 2-3 times higher than before. So it looks like there is not much room left for us in terms of optimizing the current operation with the current amine. So as a initiative engineer, let's see, I've gotten a great idea of trying how would the unit perform with a different amine. So instead of DEA, a very popular blend for deep CO2 removal or simultaneous removal of H2S and CO2 is MDA with piperazine. And that's what we're going to do in the next step. So I'm going to save all these files I've created and close them. And now we're going to take this DEA base case and turn it into MDA piperazine base case. So I'm going to save it as, and I'm going to name it MDA piperazine base case. And now we're going to do this dramatic change in reality, or make seem really easy in ProMax. So I'm going to go to active environment, which is the first step I need to do because I don't have MDA and piperazine in my list of components. So I'm going to add them. And now we're going to transform this simulation into MDA piperazine case. So I'm going to open this makeup block, which is what controls my amine composition. And I'll go to process data, open this table. I'll delete DEA. And instead, we're going to have 48% of MDA with, or say 42 with 8. That's quite typical for deep CO2 removal. So this is our starting point. One more step I'm gonna do is adjust the recycle gas because we still have DEA here. So I'm just going to copy these residuals of H2S and CO2 so I can put them back. And now I'm going to clear the composition, put H2S and CO2 back, and assume that the rest of this is 50% water, 42% of MDA, and 8% of piperazine. Of course, this is not exactly 100%, so ProMax is going to normalize it for me. And in this first step, I'm just going to execute this part to see what it does with the air cooler and if it's able to cool it down to reasonable temperature. 52.6, it's slightly worse than before, but I'm quite happy with it. So let's execute the absorber. Very often I'm getting a question on how we can come up with some initial circulation rate, some initial point, initial design. So what I like to do, if we take a look at the rich loading now, it is 0.36. For MDA and piperazine, it can be higher than that. I would say 0.45 is still reasonable. And so what I'm going to do, I'm just going to take 0.45 divided by 0.36. And so it's 1.25. And 110 divided by 1.25 is 88. So I would say that around 90 is probably a reasonable circulation rate for this new blend we're using. After this, I'm going to, again, execute this part. For this lean-rich heat exchanger, I'm going to deactivate the solver for a bit because it takes a while before it converges. So I just want to see what's the fraction over design with the current composition. I've just received a couple of questions. No worries, I will answer those at the end of the webinar. So thanks for posting them in the chat. There will be a time for answer these. Okay, so if I open the lean-rich heat exchanger now and I solve this rating, we'll see that the fraction over design is minus 61%. So it looks like with this new blend, it's not really working really well. So what I'm going to try in the first step is decreasing the feed temperature to the regenerator and see how it affects the fraction over design. So it is going to be one more iteration. I'm going to act as a solver now. If we solve it, we can see minus 55. So that didn't really help as much as we hoped for. So let's take a look at what is actually the problem here. We can see the overall heat transfer coefficient is 187 watts per square meter and degree Celsius. If we take a look at the shell side, here the film heat transfer coefficient is quite high, so it's probably not the limiting side. But if we take a look at the tube side, here we have 335. So this is the limiting side for us. And here you can clearly see why. If we take a look in this table and the velocities and Reynolds numbers in the tube side, you will see that there's simply not enough turbulence to have reasonable heat transfer. And we would like to increase velocity here. So do you have any suggestions how we can increase velocity of this one-pass heat exchanger? Plug some tubes. That's an interesting answer that could definitely work. At the same time, we would be sacrificing part of the area we're having. So what might be doable, even though it would of course mean some cost, is to use some sort of turbolizer, for instance, on the tube side, maybe plug some tubes. What I'm going to use here is using multiple passes, which would probably be a little more complicated in terms of doing the adjustment, but it could still probably be doable. As ProMax is telling you here, if we increase number of passes, it decreases the net flow area, and so it increases both pressure drop and heat transfer. So let's see what happens if I increase the number of passes to 2 and solve the rating one more time. If we go to results, we are still at negative numbers, but it's getting closer to 0. So I would say we are on the right track, and we might be able to activate the solver one more time and let the whole flow sheet execute. Okay, so while we're waiting for the results, I'm going to answer some of the questions we have here. One question was, what means sporadic corrosion and how it's monitored in ProMax? So the sporadic corrosion issues is something that our hypothetical client operating this unit is experiencing. And the way how you can get an idea about the risk of corrosion in ProMax is to take a look at ridge loading, because ridge loading is something that there are recommendations for. And if you compare the actual value with the recommendation, you can see if you are at risk. Originally, with the DEA, we had the ridge loading of around 0.45, if I remember correctly. The typical recommendation for DEA is around 0.35. So we were operating slightly above that, which was probably the reason why the lean rich heat exchanger was plugging a bit more often than we would hope for. The other question we have here is, why not DEA with piperazine? Is there any specific reason? Well, that could probably work in terms of improving efficiency towards CO2 removal. The reason why we want to use MDA with piperazine here is that MDA has a lot of advantages over the other amines. For instance, it is not as corrosive, so it can be used at higher ridge loadings, which is something I also did here. I actually allowed ProMax to run at higher ridge loadings. It is also, it can also be used at higher strengths, which means that you can have lower circulation rate, which is also something we can see here, because instead of running at 110, we are running at 90. And very often MDA is also considered advantageous because of the lower heat of reaction with H2S and CO2. So it is easier to regenerate. To some extent, this is kind of mitigated by the fact that we are using piperazine together with MDA, because piperazine, on the other hand, has a rather high heat of reaction with CO2. So these two kind of balance themselves in this specific blend. But overall, MDA and piperazine is very popular, and I've just told you the reasons why that's the case. Okay, as you can see, the dramatic change also means that the simulation takes a little longer to converge, especially since we have all these equipment or heat exchanger rating included in the simulation, but I'm pretty sure we will soon get there. All right, so the results are in, and we can see we are well within the specification, maybe even too much for CO2. So there's definitely some room for optimization, but we are meeting the specification. And if we take a look at the approaches, now the rich approaches are around 70. So it looks like the process could be more stable than before. The lean approach of H2S is also a little lower, not by too much, but it looks like we're again safely below the specification. So it shouldn't be it shouldn't be worrisome for us, I would say. Now let's do the same exercise as before for these cases when we have some fluctuations in sour feed or when we have a hot day. So I'm going to save this. And I'm going to copy it 2 times again and do A and B. So let's see how the unit performs if we have 115. That's the first case we're going to run. And we're also going to see what happens if we have really high temperature on a hot day. Looks like this absorber has some problems converging. So let me just change this convergence setting to see if it helps. It actually seems to be fluctuating, and in cases like these, what you might want to use is this K-damping factor. If you take a look at what's this, it helps to break oscillations. So I'm going to try to increase this to the value of 2 and see how it helps. Okay, that looks better. So this time we're going to start from the hot day case while the other one is still solving. And as you can see, even if the temperature is 35 degrees Celsius and we have quite high temperature of our lean amine, we're still able to meet specification. It is still true that this means unfavorable equilibrium for the reactions, but because of the very effective CO2 removal by piperazine and the advantages of MDA, we are still able to meet this specification. So stable enough, at least for the hot day. What about the fluctuations? Here we are closer to the specification with H2S, but as you can see, overall still meeting the specification even at the higher flow rate. So I'm definitely not saying this is a perfect solution, but that's a nice thing about ProMax, that there's basically no borders to imagination or to creativity. And you are able to, or you have this powerful tool to investigate various scenarios, ask yourself what if, and see how it works as a whole, including the equipment. For this specific case, we could probably tune the piperazine amount, maybe play with the circulation rate and a lot of other factors to see if we can get a better solution. And that's where we were getting to the point where I would like you to really encourage you. If you have a case like this, if you are either operating a unit or need to debottleneck it, you are wondering if you could increase the capacity, you would like to optimize the operation, you are troubleshooting something, do not hesitate to reach out to us. That's something that we help our customers with on a daily basis, and it is part of our free services that are included in the cost of the license. So I would really like you to reach out to us if you need any help. And it also applies for engineering companies. As you could see, ProMax can tell you a lot about the stability of the process, which is even more important in design when you want to make sure that the unit you're designing is going to work properly, even if there are some problems. So you can basically use it for many cases, many different units, and I would be very happy to help you with these sort of conceptual studies, trying different amines, playing with the process conditions, and trying to get to some optimum. Can you please show us again how you calculated the lean MDA flow rate when you switched to DEA, from DEA to MDA? Sure. So what I did is that I looked at rich loading, which is calculated in an analysis in this rich amine stream. If you go to analysis, here is an amine analysis created for us, and one of the results is total acid gas loading mole per mole, which basically is a fraction of the moles of H2S and CO2 combined, and this is divided by the moles of amine. And by amine, I mean MDA and piperazine in this case. And originally, once I switched, since I use a higher strength amine in this case, I had a lower rich loading value than before. I had 0.36, and I wanted to increase it to somewhere around 0.45. And since 0.36 is around 80% of 0.45, that gives me a very rough estimate that I need to decrease the circulation rate to around 80% of the original value. So I did 80% of 110, which was 88, and I rounded up to 90. So Katalin is asking about how often you must to add piperazine in the MDA solution from the unit. In terms of the applications, it is typically used when you need to remove CO2 to some lower levels. If you use just a little of piperazine, it can be very effective for bulk CO2 removal together with MDA. If you need deep CO2 removal, so in this case, for instance, we were removing what was originally 3% sour feed down to ppm levels of CO2. In that case, you very often see piperazine amounts of between 5 and 8%. So CO2, generally piperazine is used for CO2 removal in addition to MDA. And regarding the second scenario, so the piperazine losses or consumption, if we take a look in this makeup stream, this is basically because we have a simulation at a steady state point. This is telling you how much of amine you're losing in the acid gas and in the sweet gas. And you can see that we are losing more piperazine than we do for MDA, even though we have less piperazine in our blend. So that gives you an idea that the piperazine losses are rather high. They are higher than the losses for MDA, which means that you need to add it to the process at rather or relatively high rates. We have another question. In the hot days, is it possible to have spike on H2S content of treated gas due to lean amine temperature increase? Yes, definitely. The lean amine temperature affects absorption for multiple reasons. First of all, the absorption generally is favored, the physical absorption is favored at low temperatures, plus we have the effect of chemical reactions that are part of the chemical absorption, and that their equilibrium is less favored at higher temperatures. So high temperatures is definitely not desirable, and it can affect the absorption significantly. Another question is, do you have a case where you need the bottlenecking of stripper column? There are multiple ways or multiple things to take a look at for stripper columns. First of all, it might be fraction flooding, for instance, if your column is flooded. But what's also important to look at is the temperature profile. Because if you are too cold at the top, typically if you are getting temperatures around, say, 90, you know that most of the stripping is happening towards the bottom of the column. One other indication of this is take a look at the vapor stream coming from the reboiler and see how much H2S and CO2 you have here. Especially CO2, if it's present at high concentrations, can be very corrosive. And so the corrosion can kind of eat your reboiler together with the bottom stages if the stripping is happening too much in the bottom, if you have too high concentration of H2S and CO2 there. So that's something I often see, and maybe something I could have mentioned also for this specific case. 0.3 is still a good value, but if you see values over 1%, it might not be an ideal operation, and you might want to increase the reboiler duty to decrease the CO2 concentration here. I would like to just conclude the webinar real quick with a few bullet points. So as we could see today, ProMax can help you identify and potentially get rid of some bottlenecks in your amine systems. And it is really easy to investigate a countless number of scenarios. So, process conditions, we saw, various flow rates and temperatures. We can play with equipment like trying tube passes or maybe plugging some tubes. We can try different amines. So, MDA piperazine, some people suggested we might use DA and piperazine. Well, why not? I'm going to share the simulation with you. You can definitely try DA with piperazine. It would be interesting to see how it compares. Or you can play with, how much piperazine you're using. There's a lot of things you can easily put in ProMax and see how it compares. And the last and the most important take-home message from today is, please do not hesitate to contact us if you need to build a similar model or perform a similar study. This is something we do very often, and amine sweetening is probably one of the areas where we have the most know-how in, and we're always willing to share this know-how with our customers. So I just hope that you will reach out to me and that we can work on an interesting case like this in the following weeks and months. If you have any general support questions, you can always send us an email at support@bre.com. Thank you again. It was really great having you all here and seeing all the thoughtful questions. And I wish you a good rest of the day, and I hope to see you at many webinars to come.